Okay, so here's the good news about the vector addition stuff we'll talk about today. Very little of it will be new. Okay, this is all going to be pretty straightforward stuff. Okay, so we'll look at what collinear vectors are. Okay, and we may even get to perpendicular vectors. Okay, so something goes east and then it goes north. Okay, calculate its total displacement. Right, so there's going to be simple vectors like you had in Science 10, and then we might move on to slightly more complex vectors. Okay, right angle or perpendicular vectors from there. Okay, so collinear means that they are on the same what? Linear means line or plane. Okay, so these are vectors that are along the same plane, forward and backward, north and south, right and left, up and down. Okay, anything that's basically just got a positive or a direct opposite negative value. That's what collinear vectors are, and you've already dealt with those. Okay. The other things we need to look at are the basics of all types of vector addition. The basic premise of all types of vector addition is that we add vectors by placing them tail to head. Okay? That is, we draw a picture of the trip in question. So if I said to you, somebody walks 10 meters left, I would do this, and then walks 7 meters to the right, that would be my tail to head vector drawing, okay, or vector diagram, right? I have drawn the tail of the second vector onto the head of the first vector because one happened after the other. Okay, so I'm kind of telling a story with arrows when I draw a vector diagram. This happened, then this happened. Okay, what we never want to see is that somebody went 10 meters to the left and then went 7 meters to the right. If I put them tail to tail, what does that say that person did? Sort of. It says they split in half and went in 2 different directions at the same time. Okay? Because my starting point is, like both vectors have a common starting point. That means they happened at the same time. That can't happen. Okay? First they walked 10 meters, then they walked 7 meters. Okay? Tail to head. Right? Similarly, I can't draw them head to head because then it said that person started from 2 halves and walked towards itself, which also didn't happen. Okay? So we just have to be mindful of that. Does that make sense to everybody? So tail to head, draw one after the other, okay, kind of in chronological order. Okay, all vector quantities obviously have magnitude and direction. You learned that in Science 10. We reviewed it day 1 of this course. Okay, and all vector quantities are added in the same way. It doesn't matter whether these are displacement vectors, velocity vectors, force vectors, acceleration vectors. All vector quantities are added exactly the same way. All that's different at the end is what units you put on. Okay, so if you added 2 displacement vectors, your final units would be meters. If you added 2 velocity vectors, your final units would be meters per second. 2 force vectors, newtons at the end. Okay, it's all the same mathematically. All that changes is what your units will be. Okay. Okay. So from the first day, not last day, from the first day, okay, remember that a vector quantity deals with both magnitude and direction. So direction is an important characteristic of vectors, which is why we use arrows to represent them. Okay? Whatever direction the arrow is pointing is the direction the object is going. Okay? So that's pretty straightforward. The other thing about vector diagrams is the length of your arrow has to represent the scale, okay, or the magnitude of the thing that you're drawing. You can see that when I first did this diagram over here, okay, my 7 meter vector was not as long as my 10 meter vector. The length of the arrow represents the magnitude of that point. Okay? Now, do you have to measure it out and make sure it's perfectly to scale every single time? No, that will take forever, and in the end it's not worth it. Okay? So rarely does a diagram and a problem come down to whether you drew it to scale or not. Okay? Is it roughly to scale? Yes, then it'll work. Okay? But if you mess up and you have a 7 meter vector that's twice as long as your 10 meter vector, your answer is not going to agree with your picture. Okay? So you do have to make sure you're at least reflecting the scale somewhat in your drawing. Okay, so the direction of the arrow gives the direction of the vector. Okay, so we can see in this one here, we have a 2 kilometer long vector, and it is angled 30 degrees north of east. Okay, or above the positive x-axis, whatever they decide the direction. Well, they've got a compass here, so it'll definitely be north of east. Okay, now why did I say it like that? North of east. Why didn't I just say northeast?
Northeast is like directly in the middle of almost.
Exactly. Northeast is 45 degrees. Okay? Sure, this is the northeasterly sector, okay, of a compass, for sure. It's traveling in a generally northeasterly direction, but that's not accurate enough. Okay? I need to be able to tell somebody, face this way and go. Okay? If I just say northeast, they've got 90 different directions, or 89 different directions they can choose. Okay? That's not very useful. Right? I need to tell them it's this many degrees, so face east, and then move this many degrees north of east and go, and you'll get there. Okay? And that's what we do, and that's what a compass would read. Okay? All of that kind of stuff. All right? So I say it's north of east because I'm moving north in a northerly direction from facing east. Okay? If I said east of north, okay, then it would look like this. I would go in an easterly direction from north. Okay? Those two are obviously different. Okay? One's 30 degrees east of north, the other's 30 degrees north of east. They obviously don't point the same direction. All right, and the other thing, like we said already, our arrow needs to represent is the magnitude. So a 2 kilometer arrow would be that long. Okay? A 1 kilometer arrow would be that long. Roughly to scale. Doesn't have to be exact, as long as it's roughly to scale. Everything will work out on your diagrams. What screws people up more than the scale on the length is the scale on the angle. Okay? Lots of times I give somebody a 30-degree angle and they draw a line like this. Okay? Again, your diagram.
Now, could we start with grade 12? So all grade 12s, A through D, as in dog. Could you please come down to get your picture taken? That's A through D, grade 12.
Okay, your diagram needs to represent the numbers that you're given. Okay, if you go wild on your drawing, your drawing is not going to agree with your math. That creates a problem for most people. Okay, because what do you believe in your heart when you look at something that, if you know you've made a mistake, and your choices are, I did the math wrong, or I drew a picture wrong, which one are you going to tell yourself you did wrong? You're going to tell yourself you did the math wrong. Okay? You know what happens more often than not in this? People draw the picture wrong. They do the math 100% right. It doesn't agree with their picture, so they assume, oh, I couldn't have drawn the picture wrong. Pictures are easy. No, it's as easy as you would think. The math is the thing people don't screw up. The picture is. Okay? So they get this answer that's right, but it doesn't agree with their picture, which is wrong. Okay? So just keep that in mind. All right, so then the other thing we said here, the length of the arrow, okay, is proportional to the magnitude of the vector. Okay? Those are the principles of vector addition. We draw them tail to head, we point them in the right direction, we use their length to represent their magnitude. Okay. So, it's necessary often to add two vector quantities together, and we do that in a tail to head fashion, as I showed you already before, okay? But they're doing it here as well. All right, so we have these two vectors, okay? Our car moves 275 meters due east, okay? So that's this line here, okay? And then moves another 125 meters from there due east. Okay, what's my total displacement? Yeah, 400 meters. 275 plus 125 is 400 meters east. Okay, that's an easy one. But I drew it that way. Now, would you really realistically draw a vector diagram for that? Or you would just go, oh, and they're both east and I would add them together? You probably wouldn't bother drawing it. Okay? When it starts to be necessary to draw it is when you get this vector and you have to add it to this vector. That's when drawing becomes important. Okay? And I've got to show which way they're going, because if a person did this and then this, their total displacement is represented by that little black arrow. And that's what I would have to solve for. We're not gonna get there today, or tomorrow, because we're doing a lab tomorrow, but on Wednesday, that's where we're headed. Okay. All right, so everybody understands the collinear ones? They're pretty easy. Okay, so we got those two displacements, we just add them together, okay, because they're both east, okay? If one of them was west, then we would make one of them negative, right? Okay, if one was east and one was west, one of them would have to be negative when we add them together. All right, so we draw them always like we said, tail to head, okay? All vector addition is done tail to head, always, always. All right, now we get perpendicular. So, with our perpendicular vectors here, so now the car goes east and then it goes north. Okay, makes a right angle triangle, so we're still good to use trig, right? And everything we do, no matter how crazy, even if it's this drawing here that I drew, okay, we make perpendicular right angle triangles out of every single vector we have. Okay, because then we can use trig form and we can always calculate it. Okay? All right, so I've got a 275 east vector, that's this one. Okay, and then I've got 125 meters north. Okay? Is their distance traveled still the same as it was before? Yeah, it's still 400 meters because distance is scalar. But now, my displacement is how much and in what direction I change my position. I have changed my position from here to here. So now I need to know how long the red line is and what direction it's pointing. Agreed? Okay. Who can help me find out how long this is? I'm looking for a person's name who might have had some, years of his life dedicated to studying triangles. Pythagorean, yeah, Pythagoras, okay? He was the guy who studied triangles his whole life, okay? So I could use Pythagorean theorem to figure out how long this is, right? Mr. A squared plus B squared equals C squared, that guy, okay? The Greek geek, Pythagoras, okay? So I can use his formula to figure out the hypotenuse of the triangle. Okay? So I'm just going to take my, and say that C equals the square root of 275 squared plus 125 squared. Okay? And that will give me the total displacement. Okay, so the total displacement is 302 meters. What am I missing? I'm missing the direction. Okay. I can't just say northeast. That's not going to be specific enough. How can I find that angle? Yeah, I can use tan. Okay, I'll use trig to find it. Right? I would use tan if it were me. Okay, reason being, I was given the two sides I would use if I'm using tan. Okay, if I use sine or cos, I'm using the hypotenuse, and that's a number I calculated. If I screwed up, then I'm going to get the wrong answer for my angle as well. Okay, so it's always better to use the ones you were given. Okay, so I'm going to use tan because it's opposite over adjacent. Okay, so you do have to remember your SOHCAHTOA. Okay, sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent. Okay, so I'm going to try and find this angle using the opposite side and the adjacent side. So that means that theta will be the inverse tan of the opposite side, 125, over the adjacent side, 275. What mode does your calculator need to be in? Degree, yeah. If you're in math right now, you're going to be switching back and forth every time you come in here because usually you're in radians in math. Okay, so just make sure you're always in the right mode. Your answers will make no sense if you're in radians. Okay. All right, so tan to the minus 1 of 125 divided by 275. Okay, so my angle is 24.4 degrees north of east. Okay? How did I know to make it north of east and not east of north? Okay, I looked at my triangle, okay, and I look at the little arc that represents my angle, okay? The main compass direction it's touching is east, and the line is north of that. So I went, this angle here is north measured from east, so north of east. Okay, everybody follow me on that? Right? That sometimes takes people a little while to get in. It's north of east. All right, so my final answer on that would be 302 meters at 24.4 degrees north of east. Everybody okay with how that one worked?
Could you explain to me that why you can't just use the logic of the fact that he did 275 meters over that way first and then went north? Why can't you just use that? Why do you have to use the curve?
Why do I have to? Oh, you mean in terms of figuring out whether it's north and east? You can do that.
Okay.
I just give people a little trick.
Okay.
Yeah, if it didn't make sense to you and that way does, then go for that way.
Okay.
Yeah. Okay, just be cautious because I could have drawn this triangle this way too. Right? I would get the complementary angle, which would be east of north, right? In this case, he still went north and then east. Here he went east and then north. You're right, I follow your logic. This is north from east. So yeah, you're good that way. Yeah. Okay, so this is what we just did here. Okay, so it's the math of what we just did. I don't know why I have 24 and a half there. I don't think it rounded up. Okay, oh, because I rounded off there, that's why. All right, so we're going to look at a couple of examples here. Let's look at this one, okay? I want you guys to draw out the vector for this.
Could we have all grade 12, E?
It's a question about like the most boring town in the world. Okay, so these contestants in the snowshoe race move forward 10 meters and then untie a series of knots for some reason. Okay, and then they move forward 5 meters and solve a puzzle. And then they move forward 25 meters to the finish line. Okay, did I measure those to make sure they were exact? Do I need to? No. Okay, and I never really need to. No matter how complex my diagram gets, as long as they're somewhat to scale, I'll be good. This 25-meter line probably could have been a bit longer. Okay, the other two are fairly accurate, but the 25-meter one, yeah, it probably could have been more like that. It probably would have been a bit more accurate. Okay. So determine the resultant vector by adding the vectors graphically. That means from your graphic, your picture. Okay, so 15 plus 25 is 40 meters forward. Done. Okay, that's about as easy as they get. Okay. I'm not worried about scales here. Number 7 is a think outside the box kind of a question. I want you guys to see if you can figure it out. Drawing the diagram is important, okay? But there's a little bit of a math trick involved with it, okay? I'm gonna give you guys a few minutes on that one, right? So a car drives north 500 kilometers. It then drives 3 sequential displacements south, each of which is 50 kilometers longer than the previous displacement. Okay, so it goes like one displacement, and then the next one is that plus 50, and the next one is that plus 50 plus 50. Okay, find the 3 displacements algebraically. Okay, see if you guys can figure that one out. You're going to want to draw the diagram and then make an equation where each leg of the diagram has, you know, like x plus whatever, right? So here's what we know. If we draw the diagram, okay, we know that they went 500 kilometers north. Okay, then they came back in 3 different trips, each one 50 kilometers longer than the previous one. What we do know is they ended up, the final position of the car is 450 kilometers north. Or sorry, is 50 kilometers north, sorry. Okay, so it ended up 50 kilometers north of where it started. So the 3 parts of the trip that they're talking about, this one, and this one, which they're each longer than the previous one, add up to what? 450. Okay, they went north 500 kilometers, then they came back in 3 separate trips to a point where they ended up 50 kilometers north of where they started, which means those 3 parts of the trip add up to 450 kilometers. Is everyone okay with my logic there? All right, so here's where I've got to get algebraic. I know that 450 kilometers is my sum. Okay, the first trip I don't know the length of, so I'm just going to say it's x. Everybody all right with that? How long is the next one? X plus 50. How long is the one after that? X plus 100. Exactly. Okay, because it's 50 kilometers longer than the other one, which was 50 kilometers longer than the first one. Okay, so it's going to be x plus 100. Okay. What's x plus x plus x? 3x, exactly. Plus 50 plus 100. So really, 450 equals 3x plus 150. Can I solve for what x is? Is that the length of the first one? Can I figure out all the others then? Okay. So I'm going to subtract my 150. I got 300 here equals 3x. Well, that's pretty straightforward. How long was the first one? 100. Okay. The first part of the trip was 100 kilometers. Okay. Then 150. And then 200. Adds up to 150. Okay. That's just a math trick. It's not really a vector question. You had to do vector stuff to get to the math trick, to get the 450. Right? That was really all you needed the vectors for. Okay, I want you guys to try this one. Draw it out. Okay, it's 3 vectors. So this person walks 0.8 kilometers south, then 1.2 kilometers east, and then 0.3 kilometers north. Remember, you're doing this tail to head. So you got to draw your picture as you go. Okay, I'll give you a couple minutes, then I'll draw the picture. Then I'll give you a couple more minutes to get your question solved. Okay, we're looking for her resultant displacement, magnitude and direction. So this is going to illustrate something that's going to be important for us going forward when we're dealing with more complex vector addition problems. So first the person goes 0.8 kilometers south. Okay, then they go 1.2 kilometers east. Okay, and again, I'm not measuring these, but they're reasonably to scale. Then they go 0.3 kilometers north. All right, so there's my vector diagram. I've drawn them all tail to head. Okay, I'm showing where they go. Where would I draw a line that represents this person's overall resultant displacement? Okay.
From the top of, well, yeah, there.
From here?
To point 3.
Right, to there, right. So this is my initial position, okay? This is my final position over here. My displacement is my change in position, so it's this line. Okay, so that's going to be my overall displacement, and this here will be my vector. I could have also done this. It doesn't really matter. I could have either one of those angles, even though they're not the same. Either one of those angles with the right directions is correct. Okay, so I'm going to do it the way I originally drew it, which is with the top one. Okay. So I want to.
Could we have?
Okay, so now, if I'm looking at this, I know I need to calculate the length of my green arrow. if I want to find that, I need the two sides of its triangle. Agreed? Okay, if I want to use Pythagorean theorem and find out how big D is, okay, I need the two sides of its triangle. Well, this is what we call the x component, or the horizontal component of that triangle, because it's the horizontal part. How long is that line? It's 1.2 kilometers, because that's how far east they went. Okay? Similarly, this is what we call our y component. It's the vertical part of that triangle. Okay? How far south did they go? Okay, they went 0.8 and then they came back 0.3. So how far south of their starting position are they? 0.5. Okay, so we found their x component, or their horizontal part, and their vertical part. Okay, vertically speaking, or north-south, they've only gone 0.5 kilometers because they backtracked a little bit. Okay, so our y is 0.5 kilometers south. Okay, so now I have enough information to find both the magnitude of D and theta, its direction. All right, so to find D, I'm just going to use Pythagorean theorem. So that'll be the square root of 1.2 squared plus 0.5 squared. All right, so that overall displacement is 1.3 kilometers. Okay, so if she was able to do this trip over again and just walk in a straight line, she'd walk 1.3 kilometers. Okay? But I also need to know what direction she would have to walk, so I want to find theta. I know the opposite side and the adjacent side. I now also know the hypotenuse. I could use that if I wanted. Okay? But as I said before, I like to use the numbers I was given. Okay? So I'm going to say that theta equals tan to the minus 1 of the opposite side, which is 0.5. Okay, divided by the adjacent side, which is 1.2. Does everyone follow opposite and adjacent? How we figure that out? Okay, just in case you don't. Okay, opposite and adjacent always are in reference to the angle. Okay, 0.5 is opposite the angle. 1.2 is touching it, or is beside it, or is adjacent to it. Okay. All right. Now that I have that, okay, I'll get my angle. So second tan of 0.5 divided by 1.2. And I'm getting 23 degrees south of east. Okay, because I went this direction from due east. Right? So that's going to be 23 degrees south of east. Right? If you have the other angle, which is going to be 67 degrees east of south, you're fine. Okay, that is also correct. It just means you drew the triangle this way. Okay, and there's absolutely nothing wrong with that because 23 degrees south of east and 67 degrees east of south are the same direction. Okay, they're complementary angles, they add up to 90. Okay, everybody all right with that? Okay. So does everyone see kind of what we did there? This is going to lead us into what we call vector component addition. Okay? The vector components are x and y. There's a horizontal component and a vertical component to every vector. Okay? If we can find those, we can add them together because they would all be collinear. All y vectors would be up and down, and all x components would be side to side. Okay? So when we get to a question like this one, okay, so let's say I've got okay, if I want to find the total displacement of this object, it would be this red arrow. Agreed? Right? That's from initial position to final position. Okay. That red arrow also has a triangle. You can see I've got a triangle for each one of those vectors now. Okay? Well, this is the x or horizontal component of the 20-meter vector. And this is the vertical or y component of that vector. Okay? Similarly, this is the horizontal component of the 12-meter vector, sorry, and this is the vertical component of that 12-meter vector. And same for this. Now, since I know one side and an angle in this green triangle, could I figure out what x and y are? Yeah, using trigonometry, I could. Okay? And same with the blue triangle. Since I know the hypotenuse and this angle, I could find the two sides using trigonometry. All right. If I want to find red x, is it green x plus blue x? Right? Because in this one, I go east this far. In this one, I go east this far. If I take that blue x and put it down here, that'll equal red x. Agreed? Okay? And I go north this far and then south this far. If I add those two together, will it give me red y? Taking into account that one of them is south, yes. Okay? That's what we're headed towards, vector component addition. Finding the parts of the right angle triangles that make up every vector. Okay, so tomorrow we'll look at finding vector components and, sorry, not tomorrow, Wednesday, and adding them together. Right? That's where we're headed. We're obviously not there just yet. All right, let's start cleaning off our desktops here, okay, and get ready to go.